Welcome back to our home automation ZigBee light and switch tutorial. If you're following along with this exercise, you should have just completed the sections 1 through 10 in the ZigBee home automation light and switch exercise. And if you've gone all the way through this procedure, you now have a light and switch that talk to each other using the console in Ember desktop to enter commands that can communicate at runtime. For example, we were building a ZCL on-off toggle message and sending it from endpoint 1 of our switch to endpoint 1 of our light, targeting node ID 0. And you'll see that the attribute is changing, but you won't notice any LEDs changing because we haven't tied any hardware into the software yet. So the hardware has no idea what we want to do based on changes in the software. So now let's change that. We'll start by editing our light project. So open up your IAR embedded workbench project that you created with AppBuilder during the process of the other exercise. And once you have your light workspace open, you're going to scroll down to the module that has all the interesting code that we want to extend. And that's something called a callbacks file. The callbacks file is where you're going to add all of your custom code to the template that's been created by AppBuilder. If you've named your application MyLight, then you should see a file in this list called mylightcallbacks.c, and that's the callback C file that you can fill in. Note that you're welcome to use an external editor and do this exercise, and then go back to IAR to build the project. You should now have an example file generated by AppBuilder with no actual C code other than an empty definition of an Ember AF on-off cluster server attribute change callback that we selected in AppBuilder. So you'll need to decide what code to use to react to those attribute changes, and I've already pointed you at an appropriate callback, which allows a callback to be generated at runtime whenever any attribute of the on-off cluster's server side has changed at runtime for any reason. So the attribute ID, of course, is the attribute being changed, and the endpoint is the one being operated on by the command on the target device. Note that there may be multiple attributes on a single cluster, in which case this callback would be triggered for all of those server-side attributes. There's also a client attribute change callback if you have client-side attributes in your particular cluster. So our plan here is if the attribute is the on-off state, which is an attribute of the on-off cluster, then we want to toggle the LED accordingly based on the state of that attribute. Now that we know what we want to accomplish, one of the first things we might want to do as we get into this callback is look at the endpoint and decide if we want to react differently based on the target endpoint of this command. Although this application only has one endpoint, it is possible to configure a ZigBee application with multiple endpoints on the same node. For example, suppose you had a board with 2 LEDs you want to control individually with their own state, or even a level control device where each light has different levels. Those could be best represented as different endpoints, each with their own set of attribute data. So to make this code safe for multiple endpoints, you could do a switch case statement around the endpoint. Now in theory, I only have one endpoint, so I don't really have to do this check, but I'll show you an example check that you could perform. So we'll say if endpoint equals something, and what is that something? Well, you could certainly use the hard-coded value, which in our case is 1, and we can confirm that by going back to the light project in the Ember Desktop AppBuilder tool and looking at the ZigBee Cluster Library Configuration tab. And you'll notice that there is an endpoint 1 there near the endpoint that we configured. So you could use that hard-coded 1 value, but that's not as graceful as other methods of coding this up. So suppose we created some kind of enumeration of all the endpoints and used some kind of symbol there to represent our first endpoint. As it turns out, there's actually an API function available that does this. It looks at the first endpoint configured on the device, and it's what's called the primary endpoint, one for which defaults can be assumed if no other endpoints are defined on the device, or if there's a particular assumption to be made about the state of the device that can't be inferred from looking at other details. So the API we want here to reference that is something called Ember AF Primary Endpoint. So in this case, calling that function is going to resolve to endpoint number 1, but it gives us a cleaner way to reference the first endpoint on that device. So we'll say if it's the primary endpoint, it's the one that we care about, so we'll handle state changes on that endpoint. Now that we've determined it's the correct endpoint, we need to look at what attribute ID is being changed here, because again, you may have multiple attribute IDs. So a switch statement is probably appropriate here. given that some clusters may have lots of attributes. So we're going to switch on this attribute. So now we need a case statement based on the attribute ID for the on-off attribute. But what do we want to use here for that attribute ID? Well, you could look in the ZigBee cluster library and find the enumerations of all the attribute IDs on a given cluster. But as it turns out, there's an easier way to determine what the ID for that attribute is, and that is to look in your AppBuilder configuration, find the on-off cluster, and you'll then see a list of all the attributes displayed in the lower right under an Attributes tab. So any of them that are checked are the ones that are enabled for this configuration. In our case, the only one that's enabled is the mandatory one, on-off. You can see that it's an attribute with ID 0 that is a Boolean type whose default is 0, meaning off. So if you like, you could say case 0 here and specify that particular attribute. But to make things more readable, suppose we have a macro that allows us to remember that this attribute 0 really means something like on-off state. As it turns out, AppBuilder has already generated a large number of these enumerations already as part of its set of generated files. If you click on your callback C file, assuming you've already built it, you should have a little plus next to the C file. And if you click on that, it will expand a list of all the dependencies that went into making that module when it was compiled. One of those dependencies is a file called attribute_id.h. And if you double click on that to open it in the editor, you'll see an enumeration of every attribute under every cluster known to AppBuilder via its XML dataset at the time that you generated the project. And that XML dataset was installed at the time that your stack was installed. It will even contain enumerations for custom clusters if you've gone through our Extending AppBuilder video and added your own ZCL clusters to the database. So given that the on-off cluster is cluster ID 6, you're going to need to scroll down here because these are sorted by cluster ID. And after you get to the 6th paragraph for the attributes of the on-off cluster, you'll see the ZCL on-off attribute ID. And now you can copy-paste that particular symbol into our callbacks file and use that as the enumeration for which you want to make a case statement. Now you have an easy way to reference that attribute ID without any hard-coded constants. So if we get the on-off attribute ID that we're looking for, we're going to do some work. And the work that we want to do is to handle the LED according to the attribute state. And after we handle that case, we're going to break, and there may perhaps be other cases for other attributes, but in this case, we only care about the one case, so anything else falls into a default clause. If you had other attributes to handle at the server side, this is the place that you might handle them. So we look at the attribute, and if the state is 1, we turn on the LED. If the attribute is 0, we turn off the LED. Now we have to know what the state of the attribute ID is based on the endpoint in question. Note that this callback is being called after the attribute's already been modified by the application framework. So that means that you can determine what that attribute's value is, which you'll note is not passed on the call stack. You can determine that by going in and reading the state of that attribute from the application framework's API for attribute access. At this point, it would be really helpful to know what the API is to try to find that attribute's value from the framework. So go ahead and open your favorite browser and open the documentation index, which is a file that's installed along with your stack. For example, in the 5.40 installation, it's under 5.40 EM35x documentation index.htm. That's an index of all included documentation. You can either open it directly or you can go into the Start menu. In the Start menu, it can be found under Start, Programs, EmberZNet, the name of your stack, and then underneath that, click on Documentation Index. Once you've got that documentation index up, you can scroll down to the section that says EmberZNet Application Framework, and you may need to go into the Application Framework Documentation section. In the 5.41 releases, this is under the same doc index. In earlier versions, it belongs in a separate page. Here you'll see documentation for the developer guide, a CLI interface, and some Application Framework API guides. You can open either the HTML or PDF API guides. It's the same data, just in different formats. So we'll use the HTML and I'll guide you to the proper APIs. If you start at the top level reference and then click on the Ember Application Framework API reference link, you'll see the sections of the top level API. We want the general interface because we don't want type definitions, we don't want callbacks. We're not looking at a command buffer loading interface right now, and we're not interested in enumerations yet. So we're going to go into the general interface, and we're looking for things that have to do with dealing with attributes. Those will be in the attribute storage section. You'll see a list of APIs having something to do with manipulating attributes, whether it's reading them, writing them, discovering what's available on the device. And we're looking for something that's going to allow us to read an attribute for the server side of an on-off cluster. We see a lot of different write calls here, but let's go down to the read calls. The first one we find is Ember AF read attribute, a low-level function that allows you to read any attribute from the framework. That has a lot of parameters, but if you keep going, you'll find some more convenient wrappers around that allow you to use fewer arguments to get the data that you want. Going down one, we find Ember AF read server attribute that's specifically for reading server-side attributes on the device. So you can use Ember AF read server attribute to get you a little bit further than Ember AF read attribute without so many parameters. And that's the one that we're going to use, Ember AF read server attribute. And we can go ahead and copy paste that into our project so that we get all of the function parameters correct. We're going to paste that into our C file, make sure to add a semicolon at the end. And since it returns an Ember AF status, we're going to declare a local Ember AF status variable here in the context so that we can catch the status of the read server attribute call to be able to debug this later in case there's some kind of problem. So we'll go ahead and wrap this in curly braces to get some local context where we can declare this Ember AF status variable and assign it to the value of the Ember AF read server attribute call. We'll call it read status so we can say read status equals the result of Ember AF read server attribute. Now we begin to fill in the parameters. We'll make it easier to read by putting them on separate lines. And don't forget to put the semicolon, otherwise your program won't compile happily. And don't forget to terminate the curly braces that you added up above. Now we have a read status, and we've examined it, and then we only want to go further if the read actually succeeded, because if it hasn't, we don't want to try to update the state of an LED based on an attribute that we are unsure about. So what's the Ember AF status that we're interested in getting back in a successful case? Let's go to the API guide and find out. If we click on the hyperlink for Ember AF status, we'll get an enumeration of all the different status values that are applicable to this data type. The one that we're most interested in is Ember ZCL status success. So we'll just copy that right into our code so that we can check against it. And now we can say something like, if read status is not equal to that successful status, then we're going to print some kind of error and return. So we'll say print an error message and then return without doing any sort of update to the LED. Otherwise, it's safe to move on and we can update the LED accordingly. At this point, it would help to understand how to print error messages, so let's take a look at some of the printing logic to figure out how we're going to print that error message. Back to the API guide we go again. We can use the back button in the HTML to go back to the top of the general API reference. Now we'll scroll past the attribute storage APIs so that we can look for functions that have something to do with debug printing. We're going to go past the miscellaneous section, which doesn't really have to do with printing. And then the next section is the printing section with the APIs that we're interested in using in the application framework to handle output printing. Now this ties back to the application debug printing choices that you made in the AppBuilder setup. You'll see functions like Ember AF print off, print on, all off, print buffer, print string, Ember AF print, as well as an Ember AF print line, which adds a new line at the end. Let's go ahead and use the Ember AF print line to print a string with a new line at the end. You'll see that this is a void function that doesn't have any return value. And now you'll see we have two parameters, functionality and some kind of format string. The format string is quite similar to your standard printf that you're used to from using C programming, and we'll assume that you know how to do that from prior experience with C code. But let's dig in and understand this functionality parameter. This refers to a particular area of printing. Remember when you set up your AppBuilder printing configuration for your light and you had a number of choices about which print areas to include by default and which ones to compile in? They were listed off in different functional areas and then listed off by cluster. Those are the areas that you're going to reference as your area of functionality when you're doing your Ember AF print strings. Referencing certain areas allows you to turn those areas on and off very easily with a CLI command if they've been compiled in, or simply excluding them from your compilation altogether to remove the code space. This makes it easy to selectively debug your application with some printfs while leaving others turned off to reduce the amount of verbose output from your application. So we're going to go ahead and use the on-off print area because we need some area that's been enabled for our application, and this code is relevant to the on-off cluster. But how do we determine what Int16U value to use from the area of functionality? One way to do this is to look at the output of AppBuilder and determine what kind of code is behind that selection of the on-off print area. We can do that using something called the preview window in the AppBuilder view. So if you click the preview button, you'll see that it pre-generates a bunch of content. And one of those files that you can preview is a top-level header file that has the same name as your configuration. For example, mylight.h. If we go into that file and you look at those things, they are grouped by related areas. And if you go down to a section that says debug printing section, that has all the data around printing and debug output. This is where all the individual areas get defined. The area for the on-off printing is the one that says Ember AF print on-off cluster, which is defined as 10 hex. As it turns out, you don't actually need to reference those enums specifically. You could certainly do Ember AF print line and specify either the 10 hex or its enum and then your print string. But actually, AppBuilder goes a step further. It knows what areas you have enabled, and it actually creates macros for all of those different print APIs, allowing you to define them by area. If you look at one of the other generated files in this preview list, there's a file called debugprinting.h, and this is the file that creates all of these macros for the different Ember AF print functions divided up by cluster. And those macros, if those areas are enabled, will contain the printf functions with your print area already filled in. And if the print areas are disabled, then those macros just resolve to do nothing at all. So you'll see that in the on-off section, you have macros that will do something if printing is enabled and printing for the on-off cluster in particular is being compiled in. So now we can use these macros, and you'll see the format of these is much like the standard API without the area functionality. So we have Ember AF on-off cluster print line, as well as print, flush, and the other Ember AF print functions available to us. So we're going to make use of that macro in our code to make it a little bit more readable. So we'll say Ember AF on-off cluster print line. Make sure you use a lowercase l for that to correspond to the macro. And then you won't need to specify the area anymore, just the format string. So we'll print an error message that says error reading attribute, and then we'll print out the ID of that attribute. So we'll say 0x%2x for a 2-byte hexadecimal output. Now this is a custom format specifier that you may not have seen before. This is unique to our printf structure in our Ember API. It prints a 2-byte hexadecimal value in uppercase. We'll use this to print out the attribute ID, and then we'll put a colon and the hex value of the error that we got. So we'll say 0x%x for a 1-byte hex value of the error message. So to correspond to the %2x, we'll put in the attribute ID, and then for the second value, the status code of the read status. That should give us a printf that tells us what the error was for reading a particular attribute. Now, of course, we need to fill in the values for our Ember AF read server attribute after pasting the template in there. So the endpoint we want to look at is the same one for which this function was called. So we can really just use the word endpoint here because that was coming from the call stack. The cluster in this case is the on-off cluster, because that's the one that this callback is invoked for. And of course, you could look through the ZCL documentation or AppBuilder to try to learn that that's cluster ID 6 and put a 6 here. But here again, AppBuilder's already created a nice enumerations file for you that enumerates all the cluster IDs with some kind of friendly name that you can use in your code. So if you look in your list of dependencies of this callback C file, you'll notice that one of the included header files is a cluster ID.h. They're sorted again by cluster ID. And you'll see number 6 is the ZCL on-off cluster. So we're going to read a cluster described as ZCL on-off cluster ID. And then the attribute ID is the same one for which our case statement is written, ZCL on/off attribute ID. Alternatively, you could just use the attribute ID passed on the call stack. Don't forget that this uses a lowercase d and not an uppercase D. So we're reading the endpoint for which the callback occurs, we're reading the on/off cluster ID, we're reading the attribute ID that this callback pertains to, and then we need a data pointer into which we can read the data. And we need an indication of how much data to read because some attributes may have variable length, so it's not always clear to the API how much data you're interested in reading. Since we're reading something that's embodied by a Boolean data type, we can define some kind of local Boolean value here and then read the data right into that. So we'll call this Boolean isOn because a value of 1 equates to true, that turns the LED on, and a value of 0 or false means that the LED should be off. So we're going to read into a pointer to isOn, so address of isOn, and then the amount of data to read is simply the size of isOn. That way we don't have to worry about how large a Boolean is in your particular architecture. Now we have a way to read the attribute data into something and know how much to read, and if that read fails, we'll print some kind of error and then return. Otherwise, we'll move on knowing that the data that we have is valid. Now we know whether or not the LED should be on, so we'll say if isOn, set the LED, else we clear the LED. At this point, we now need to determine what functions are appropriate for manipulating LEDs on this hardware. Certainly, you could access the GPIO registers directly on the chip using what's available in the datasheet, but in our case, we provided a hardware abstraction layer, a HAL, with APIs that you can use to manipulate the LEDs in a manner that's generic across different board configurations. That keeps you from having to specify individual GPIOs, which may be different across board configurations. This allows your code to be more portable across hardware configurations, even across chip platforms if you have to go between one Silicon Labs NTU and another. So let's go back to the API as we did before, but instead of the application framework API guide that we've been referencing so far, we're going to go into something called the HAL API guide, which is part of the Ember ZNet API guide. The application framework is only dealing with clusters, cluster libraries, and the application level architecture, but doesn't deal with the stack and the HAL and things related to the hardware. So you're going to have to exit the application framework API or just go back to the documentation index. And starting from that index, you're now going to go down to the Ember ZNet API guide. After finding and clicking on the Ember ZNet API reference, which can either be PDF or HTML, you're going to locate the Hardware Abstraction Layer, or HAL, API reference. There's a brief introduction here that explains the conventions of the APIs so that you understand the naming conventions. So since we're looking for drivers for the LED, which is a peripheral, we're going to click on Sample APIs for peripheral access. And there are peripheral drivers for the UART, the button controls, buzzers via a PWM or pulse width modulation, and there's an LED control driver that we'd like. So if we click on the LED control driver, that gives us some functions we can use to manipulate the LEDs. There's a set of enumerations for something called HAL board LED pins, each of which is a HAL board LED, and then there are functions that manipulate those LEDs within that enum set. And we'll go ahead and ignore the HAL internal and HAL stack prefixed functions because, as the API introduction was clear to tell us, those things are not meant to be referenced directly by the application. They're meant to be referenced internally by the stack or referenced by the stack. So the ones that we particularly care about are the HAL toggle LED, the set LED, and the clear LED functions. Note that since this is an LED driver, it already understands that an LED is a diode and understands that it uses logic 1 to turn off and logic 0 to turn on. So we're going to use HAL set LED to turn on the LED and HAL clear LED to turn it off. So we'll go ahead and copy the HAL set LED function into our code. So HAL set LED on some HAL board LED enumeration. And if the attribute reads as false or 0, we're going to clear it with HAL clear LED. Don't forget to add your semicolons. Now the thing that remains is to decide which of those LED enumerations should be specified here. So let's learn a little bit more about how these things correspond to pieces of hardware. If we click on the HAL board LED pins enumeration hyperlink in the API guide, we find that the HAL board LED pins are each connected to a different GPIO on the board, and that they're defined in a file called dev0680.h. This dev0680.h is actually a template board header file that corresponds to the sample GPIO setup used on the EM35x Development Kit breakout board. When you go into AppBuilder and you use the HAL configuration tab to design your I/O configuration, you can specify your own custom board header file, or you can use the dev0680 board header or any of the other provided board headers as a template. So let's take a deeper look at what's in the dev0680.h file. If we click on the line number that references that definition, it takes us into the source code of that header file so we can see the related definitions. We can see which GPIO is tied to each pin. We have 3 individually defined LEDs, and then we have board LED 2, which is simply a macro for board LED 3 for backwards compatibility with boards that had more LEDs than this one. Then there's something called board activity LED, and that's actually invoked every time a packet is processed for incoming or outgoing stack packets. So you're not going to want to use that LED because that's already in conflict with something that the stack is doing to change the LED. If you wanted to alter that behavior, you would have to go into the led.c driver file provided in the HAL and alter that HAL stack indicate activity function used to modify the activity LED. And we don't want to use the heartbeat LED, which is on board LED 1, because that's already our red LED that's blinking to indicate that the application is alive. So if we can't use board LED 0, and we can't use board LED 1, and board LED 3 is simply a redefinition of board LED 2, then we've determined by process of elimination that the only one that's interesting to use that's not in conflict is board LED 2. So we're going to use board LED 2 to make sure that it's not conflicting with any of the other LEDs in this application. So we'll use board LED 2 for HAL set LED as well as HAL clear LED. Don't forget to save as you go. Now our LED toggling code is updated appropriately, and make sure that you can compile successfully. You can compile this module individually by right-clicking and saying compile. That'll help to check for any errors that you may have made. As you can see, I've already violated at least one condition here in the compiler by not properly escaping some of my curly braces. So after adding the appropriate curly braces to escape our if block, we've corrected the compiler error, and we can also optionally add some braces around the switch statement to make it a little clearer. And once you have the right number of curly braces to match everything up, you should be able to compile it correctly, and then you can use the project make option to build the remainder of the project. This should go pretty quickly since you already have built the project before, so you don't have to rebuild all the modules, just the ones that have been changed. After it rebuilds callbacks.c and relinks a new EBL file, you'll be able to take that new EBL file and apply that to the light. Make sure not to accidentally apply it to your switch, otherwise you'll have 2 lights. So find your light again, make sure that you're still connected, so it should show a green circle in the adapter's view. You're going to say upload application, find your My Light application, which should actually be in the history of uploaded applications. And you won't need to upload the bootloader again because it will stay resident in memory. And you won't want to erase the chip because that will erase all of the non-volatile information about the light having gotten onto the network. So if you say erase chip, you'll have to start over and form a network all over again from your light and join your switch again because your light will likely have chosen new network parameters the next time it forms. So make sure not to erase the chip, and you don't have to update the bootloader unless you really want to. Now you're going to say OK to begin the upload, and it should only go around one time to perform the flash load for just the application binary. Now we can repeat section 10 from the instructions to build and send over that toggle command from the switch to the light. And now we'll check that in addition to getting the printfs and some changes to the attribute in RAM, we actually get changes to the light. So we're going to go back to the console of each device, your switch, and your light. Make sure that you can see each of those consoles. And if you haven't closed these consoles before, you should still have something in your scrollback history that you can recall that builds the toggle command for you with ZCL on-off toggle. And now you can use the same send command, send 011, to send that toggle message. And if that process worked correctly, you should now notice a glowing red LED on the side of the breakout board when the LED turns on. Now let's go ahead and send that command again and see that the LED turns off. So we do have to build it again because every time you send that built command, the buffer is cleared. So build that command again with another ZCL on-off toggle entry and send it again to the light's endpoint, and hopefully the LED has toggled off again. And now we have the LED toggling on and off based on the state of the on-off attribute. And in our next exercise, we're going to edit the switch application so that we can get that toggle message to be initiated not by a CLI command entered manually from a console, but rather by the act of pushing button 1 on the switch's breakout board.